In this video, we will look at how we can generate various spatial patterns on grids of positions. When generating spatial models, we often need to create various complex patterns. These patterns may be made up of regular lines and polygons. Such patterns are often generated using grids of positions. The positions are typically stored in lists. These lists can be structured in different ways. Let's have a look at 3 key ways that a grid of positions can be structured. A nested list data structure is a list of lists. For spatial grid, we can use either flat lists or nested lists. The preference of one over the other is a matter of convenience. 3 very common list structures are flat lists, a list of columns, and a list of rows. The example shows a grid of 6 items. The code shows how these 6 items structured in 3 different ways. As a flat list, as a list of columns, and as a list of rows. The structure affects how positions are extracted from the lists. In the diagrams, one position has been circled. The code for extracting the highlighted position is shown. With flat lists, positions are organized as one long list. In the diagram, the bottom left corner is the first position in the list, and the top right position is the last position in the list. To retrieve a position in the grid. With lists of columns, each column of positions is stored in a separate list. The 2 indices select the column, then the position in the column. So in the example, we select the 4th column, and then the 3rd position in that column. With lists of rows, each rows of positions is stored in a separate list. The 2 indices select the row, then the position in the row. So in the example, we select the 3rd row, and then the 4th position in that row. For the remainder of this video, we will focus on flat lists, since they are the most common data structure. Note that the term flat refers to the data structure. It does not mean that it has to be flat in 3D space. In fact, the positions can be any shape. In the example, we can see a flat list containing 48 positions. The positions form an 8 by 6 grid. We can think of the grid as having a width of 8 and a depth of 6. Each position in the grid has an index, which for a flat grid is a single number. In the diagram, the grid position at index 19 is highlighted. The actual position may have some other ID. To get the position out of the list, index notation can be used. It is hard to work with flat list indexes. Usually, when writing code, we prefer to think in terms of a coordinate location. We can use the letter I and J to specify a coordinate location. For example, the highlighted position would have a location of 3 to 2. We can convert a coordinate location to a flat index using some simple maths. Here we show how to convert the location of 3 to 2 to a flat index. Note that the formula requires a width of the grid. In this case, the width is 8. In order to make it easy to work with coordinate locations, we can create a function. The function can convert the location to a flat index. We will use this function in some of the later slides. From any particular index, you can move to other neighbouring indexes. You can think of it as moving up, right, down, and left. Here are the 4 directions of movement. To move to the right or left, you can add or subtract 1 from the start index. To move to the up or down, you can add or subtract the x width from the start index. These movements can be used to get the positions to draw shapes on the grid. Let's have a look at how to create a quad shape. When creating a shape, it is convenient to always start at the bottom left-hand corner of the shape. This will make it much easier to avoid going out of bounds. We will call this the origin index. In the example, we can see that the bottom left-hand corner of the quad is index 9. To get the other 3 indexes, we can use the movement rules. To move right we add 2. To move up we add width 2 times. And to move left we subtract 2. Let's try another example. This time we will draw a hexagon shape. The origin index is again index 9. Notice that this time, the index is not actually on the boundary of the shape. This is not a problem. We can still start at this index. This time, we can get 6 other indexes using the movements shown. Using these 6 indexes, the 6 positions of the hexagon can be retrieved. The quad and hexagon patterns can be implemented as functions. This will make it easier to create quads and hexagons on different grids. Here is the code for the quad function. And here is the code for the hexagon function. We will use these functions in some of the later slides. Let's see how we can generate multiple shapes on a flat grid. Here we want to fill our grid with quads. The quads will be spread out so that in the horizontal direction, the gap width is 2. And in the vertical direction, the gap width is 1. In order to generate the 4 quads, we need to find the 4 origin indexes. To find the origin indexes, we can use 2 range functions. The parameters for the 2 functions are shown. Note that for the horizontal direction, the step width is 4. And for the vertical direction, the step width is 3. This is because the gap between the quads is larger in the horizontal direction. Also, note that for the end parameter of each range, we have subtracted 2. Our quad is 2 units in width and depth. Subtracting 2 ensures that any quad that gets generated will never go outside the extents of the grid. Doing so would result in the wrong index being returned, or would result in an undefined value, which may result in subsequent errors and bugs. The 2 range functions can be used to calculate a location in the grid. The flat index can be calculated from this location. In the example, we see that one of the locations is 4, 3. A flat index with a value of 28 can then be calculated. The actual position can then be extracted out of the list using this index. Here is the code for generating the 4 quads. The code consists of a nested for each loop. Each time around the loop a new origin index is calculated and a quad is generated. In the example code we only show the process of getting the 4 indexes for each quad. In order to draw a polyline, the positions would have to be extracted out of the list using the indexes. The polyline could then be generated through theses positions. Quads are quite straightforward. Let's look at a more complex pattern, close packing of hexagons. Next, we will look at how to pack hexagons. The method that we use here can be applied to any shapes. For hexagons, the pattern is a little more complex, because the hexagons pack together and interlock with one another. This pattern actually consists of 2 separate patterns. We refer to them as the A pattern and the B pattern. The same approach as before can be used for finding the origin index of each hexagon. A nested for each loop can be created to get the bottom left location for each hexagon. The flat index can then be calculated from the location. The diagram shows 4 of the hexagons in the A pattern. We repeat the same process for the B pattern. Here is the code for generating the A pattern. The code consists of the same nested for each loop as for the quads. The arguments to the range functions are different. And in this case, we call the hex function instead of the quad function. And here is the code for generating the B pattern. Compared to the A pattern, the only difference is in the first argument to each range functions. When we combine these patterns, we get the expected close-packed hexagon pattern.